It'd also be like a cusp or something?
No, because then the derivative wouldn't exist there.
Right.
So because we got 0, right, that would throw that out, yes.
Well, it can't be a solid point because...
Can't be a what point?
It can't be a solid point because the multiplicity of it is 2. It's an even multiplicity.
But now you're relying on it being a polynomial, right? Yeah, so again, we're talking about generalizations, right? If we want to say, okay, we're only looking at polynomials, we only have this scenario, then then of course, yes. But do you really want to be doing that for every function, like figuring out if it falls into this one special category, right? So in math, we try and get the most we can get with the least amount of information, right? For any function that's continuous on a closed interval, here's how we find the absolute max and mins. If you want to go find local max and mins, if that's what you want to do, don't do this. This is not efficient for finding local max and mins. What's efficient for local max and mins is to have plotted all those numbers on a number line, created regions, got test points, plug those test points into the derivative, and then figure out if you're going up, then down, then up. And then from that, you can figure out your hills and valleys. That's the most efficient way to do it. Not to try and categorize. It's just not efficient. That's all. Okay? Hold on. Let's move. I want to at least not lose track of where I am here. Okay. What was your question while I erase this?
So with this idea of finding the absolute like global max and min on the closed interval.
Yes.
If you're not on a closed interval, this is obviously not going to work in every instance, but couldn't you, for something where it's just, hey, here it is, it's some function, couldn't you utilize the limits as it approaches negative and positive infinity to figure out, to say whether those could be a max or a global max or min? What
my function does at the ends still doesn't dictate other things that may happen on the interior, right? I mean,
like,
yeah.
If it's, it does that and it just goes to 0, your limit would tell you, oh, it just goes to 0, well, that would be your global max.
Like I said, I think that there's more efficient ways. Look, in Cal 1, there are 2 methods, okay? The closed interval method, which is what I just showed you. With the closed interval method, you can find your absolute maxes and mins. If you want to go find local maximums and minimums, you use the open interval method, which is to find your critical numbers, put them on a number line, partition your number line, test points into the derivative, and figure out where you're going up, down, up, down, up, down. That's the most efficient way to do it. It covers all scenarios, and so that's why it's taught that way. Okay? All right, now, in what we were just doing, right? Last class and the beginning of today, our functions that we were looking at, we were using the second derivative test. All we were doing was finding the hilltops and valleys of these surfaces. We were not trying to find the absolute highest point and absolute lowest point. If we're going to attempt to do that, we must do what we did in Cal 1, which is close the interval. But that's a little problematic because what do we mean by close the interval? In Cal 1, it's just our domain, right? In Cal 1, our domain is on the number line, x-axis, so we just go from A to B, we close it off, and we're good. But here, our domain is actually on the ground, right? It's on the xy plane. Those are the values that are being plugged up into the surface. So what do we mean by closing off that domain? So the first part of this is just to make sure we get some language understood, and that is the difference between a closed set in two-dimensional space versus sets that are not closed. So a closed set is any set that has we're talking in two-dimensional space. So imagine this is on the ground, right? This is like the xy plane. A closed set is going to contain all of its boundary points. So every point along this boundary is contained in the set. So it's like in Cal 1 we have open intervals and then we use the brackets for closed intervals, right? Closed here means that every point on the boundary is there, right? That's what it means to be a closed set. Anything that is not closed, or these are examples, this is dotted around the edge. So that would be like a disk that does not include the boundary. That would not be a closed set. You could have a disk where you have every point on the boundary except one. You're missing one point. That would not be a closed set. And then you could have something where you have, part of it's closed, the other part's open, like this. That would not be closed. So I'm not talking about closed versus open here. I'm talking about closed versus not closed, right? Closed versus not closed. That's the first concept we need to understand. The next concept we need to understand is what it means to be a bounded set. A bounded set, definitions here, in two-dimensional space is a set that is contained within some disk. So if you give me a set, two-dimensional space, like that, if I tell you all the points in here, and let me say including the boundary, that would be a closed set, and it would also be bounded. It would be bounded because there's a way I can draw a disk around it, and that region is within my disk. If you just think of like half of a sheet of paper, right? Take like the XY plane, or let's just do the first quadrant. Let's say all the points in the first quadrant forever. Let's include the boundaries, the X and Y axis, all those points. That would not be a bounded set, because there's no way you can draw a disk around it and contain the whole thing. You're going to find points outside of it. So this next theorem that we're about to get requires that we are restricting our function to a closed bounded set. If you don't have those conditions, this theorem falls apart, and you get into what are called boundary value problems, which are actually really, really strange. And y'all have heard of Ted Kaczynski, the Unabomber? He was a mathematician. Did y'all know that? Before he went he was a mathematician. He was really deep into the boundary value problems. So don't go study those. So we are being very specific to avoid these weird things that can happen when you have these open sets. Closed sets, bounded closed sets, let's stick with that. All right, so let's look at the theorem. The extreme value theorem. So this is exactly the closed interval method I just showed you, but for surfaces. So first of all, it says, if your function f is continuous, right? That means you don't have any crazy asymptotes or like all of a sudden the function disappears. As long as it's continuous, so your surface looks nice and like a sheet flowing in the wind. As long as you've got that, and that it's defined on a closed bounded set. So the domain of it, like if you look at the domain on the ground, you have a closed bounded set. Then if you have that, then your function must attain an absolute maximum value and an absolute minimum. It has to have a highest and lowest point. See how this is very much like Cal 1, right? Except instead of a curve, it's a surface. Now, to find the absolute maximum minimum values, to find them, here's what we're going to do. First, we're going to find the values of f at the critical points. So in the previous problems we were doing, first step was to take the partials, right? And set them equal to 0. And that found us our points. Those were called critical points, right? We're going to do the exact same thing we did in those other problems. We're going to find the critical points. Okay? That's step number 1. Find the critical points. Step number 2 is now what we're going to do is we're going to, let me back up, hold on. I left something out here. We're finding the value of the function at the critical point. So first we find the critical points, right? First we find them, and then we plug those into the original function. That's kind of like what I had over here when we were like, okay, we're going to take the original function and we're going to plug in those 4 values we had, right? We had the 2 endpoints, and then we had the 2 critical points, critical numbers. The first step of this is that critical number part. You find the critical numbers and you plug them into the original function. The second part of this is plugging in you know how we did the 2 endpoints? That's the second part of this. You have to find the extreme values of the function on the entire boundary. Somehow we have to go around the boundary of the region and see what that function f does on that boundary. That's going to be the hardest part of these problems. This first part we've done already. We're kind of comfortable with this. The second part we have not done. Once we do those, We just compare the answers we get, and the biggest value we get out is the max, and the smallest we get is the minimum. So let's do an example, and then once we do it, hopefully you'll see how this all goes together. So I'm going to let you read that first. Find the absolute maximum and minimum values. To reiterate, this problem like this will not be on the test next week, but it will be on your final. Find the absolute maximum and minimum values of this function. Okay, so here's a function of two variables. I want to find the highest and lowest points for that function on the closed triangle with these vertices. All right. So let me start by let me see if I can first figure out what the domain of this function is. See, because this is a surface, right? Right here, this is a surface. Show it to you right here. That's the surface, okay? That's with no restrictions. That's what that surface looks like. But see, I don't want to look at this surface on the entire thing. I want to restrict it onto a closed bounded set. The closed bounded set we're talking about is the triangle with these vertices, all right? So let me show you this. I'm going to show it before I actually do anything on the board. This right here is a two-dimensional picture of that domain. So if we talk about the ground, right? Here are the vertices. This was the point 1, 1, 0. And then this one was 1, 4. And then this one right here was 5, 0. Okay. Okay, I gave you that information, right? This right here, in the problem it said, what's the absolute maximum minimum value of this function on this closed bounded set? There's the triangle. I'm only taking the points in that triangle and I'm mapping those from the ground up into the surface. So now on the right, you see that same picture of that triangle, but on the ground. You see it? And now here I'm going to bring the surface in. Here's the surface. That's the entire surface. And now I'm only going to allow myself to plug the points in the triangle into that surface. If I do that, I get just that green portion of the surface. Do you all see how that is working? Yes? If I look at it from the top, the green portion is actually, looks like it's the same as the orange because it's just those points getting plugged in, which means I can completely eliminate the original surface. I don't even need it anymore. And so what we're trying to determine is on that green surface, what is the absolute highest point, right? Where are my points? What are the highest and lowest points, right? That's what we're trying to figure out. All right, so that's the visual of what we're doing. Now, how do we actually do it, right? So the idea is this. If there's an absolute max or min, if there is, it's either going to happen at a point in here, right? It's going to have to be at a point somewhere in here, or it's got to be a point on the boundary. One or the other. So the very first step of this is to act like there is no boundary and find our critical points just like we did in the previous examples. And just see if we get a critical point that lands in here. Okay, so let's start with that. I need my function. All right, first thing, I'm going to take my partial with respect to x, which is going to be y minus 1. Nice. Now I'm going to take the partial with respect to y, and I'm going to get x minus 2. Oh, even better, right? And now I'm going to figure out where these are both 0. So this partial is 0 only when y is 1, and this one over here is 0 only when x is 2. So the only critical point I have is the point 2, 1. Okay? Nice. These are nice partials, right? Now, before I do anything else, I need to go back and talk about my triangle. It was the point 1, 0. Wait a minute. What was it? 1, 0. Oh, it's right there in front of me. I'm sorry. 1, 0. 5, 0, and 1, 4. There's my triangle. I have to make sure that this point lives in that triangle. If it doesn't live in that triangle, then I'm not going to throw it away. In Cal 1, this would be like if one of your critical points that you found was outside the interval that we were looking in, you just throw it out. So I got to make sure that this lives in here. Does it? I think we can, without too much, right, we can determine that's in there, 2, 1. So I need to actually figure out what's going on here. So I'm putting a little check mark, just that I actually did check that it lives in there. So what do I do with that? I take it and I plug it into the original function. I'm not calculating capital D, right? I'm not doing any of that. I'm just figuring out what is the value of the function at this point. So I now plug it into the original function. 3 plus, okay, x times y, those two multiplied is 2, minus the x, which is 2, minus 2 times the y, which is 1. What do we get there? 1. When I plug in 2, 1, the function spits out 1. Yes?
How do you check if the critical point is within the boundary?
In this particular case, it's just a visual check because it's the 0.21, right? 1, 2 is here, and then if I go up 1, it's right there. I'm convinced that it's in there. Now, if it would have been like something like 4, I don't know, 1.2, how would you check that? You would have to look at this as a line segment and then do like some sort of like check to see if it's below or above like we did when we did inequalities, something like that. I don't think you're going to run across anything in here where you're going to have trouble figuring out if that critical point is in there. It's just remembering to check. That's going to be really the thing. If it's not in there, it'll be obvious. If it is in there, it'll be obvious. Just don't forget to check. All right. This right now tells us absolutely nothing. I do not know if this is going to be the highest point on the graph, the lowest point. It cannot even be a highest or lowest point. It just, if there is one, this could be where it happens. Yes?
So, question feeding off of what he asked, what if you have a max or min that happens to lie on the border of your domain?
That's exactly what we have to check now.
Oh.
We've only done the first part of this. All we've done right now is check the interior, and we said if there's any maxes or mins that are going to occur from the points in here, the only place that matters to us is the 0.21. Okay? But now we have to check the boundary. And this is the hard part, all right? You ready? This is going to be different than anything we've done before. So step 2. Let's say all of this right here was step 1, all right? If you look back at the steps I gave you here, right? The first step, find the values of f at the critical points. We just did that. Now we're going to find the extreme values of the function on the boundary. So step 2. Let me show it to you visually. Yes, you have a question?
Oh, no, it's
I want to show it to you visually first. All right? What we need to do is we need to look at the value of this green surface. We need to look at the values along the boundary. But the boundary is a triangle, right? So how do we do that? First thing I'm going to do is I'm going to not look at the whole triangle. I'm first going to only look along this edge. Because if I look along this edge, and this edge alone, I know something about every point on this edge. They all have the same y coordinate, don't they? And the x coordinate actually just goes between 1 and 5, right? But every point on there has the same format. It's going to be some x value. The y value will always be 0, right? Because this is a terrible graph. This is the x-axis right here. Do you all agree that every point in here is going to be x0, that's the format of the point. And I also know that the x here has to be between 1 and 5. And over here in this picture, can you all see if I just restrict myself to that line segment from there to there, that the outputs create a line. And so what I need to do is figure out the highest and lowest points on that line. So it's almost like we've reduced the problem to a Cal 1 problem where you're looking at it from this perspective. You have a closed interval, right? And then you have some function. You're trying to find the highest and lowest points. Let me say it again. We've now turned this into a Cal 1 problem where it's like a flat sheet of paper. You have a closed interval and you have a function. And can we find the absolute max and min value of a function on a closed interval in Cal 1? Yes. We're going to have to follow that procedure now. And we're going to have to do that for each edge of the triangle. This is going to be 3 different problems we have to do. All right? That's the setup. Let me actually do it now. So what I'm going to do here is I'm going to draw my region again. This was the point 1, 0. This is the point 5, 0. This is the point 1, 4. Okay, I'm going to label these segments. All right? I'm going to call this side L1. I'm going to call this L, let's do L3. Let's call this one L2. All right? So I'm about to set up 3 different problems where I'm going to go along each boundary. So let's talk about L1 first. On L1, here's what's happening. Every point, like we just said, every point along L1 has the format x0 with x being between 1 and 5. Does anyone have a question on that? That if you're on L1, your point must look like that. No questions? Well, if every point looks like that, then I should see what happens if I plug a point like that into the original function, right? What does that function do to a point that looks like this? So let's do it. What does the original function look like if you plug in x for x and 0 for y? Well, let me see. 3 plus 0 minus x minus 0. So just 3 minus x, right? And so just take a step back. Is that not a function of a single variable? Right? That's a function of a single variable. And it's defined on a closed interval. So how do we find the max of this in min? We take the derivative, right? Critical. Now it's a line, so I think everyone would agree that we're going to have max and min at the endpoints. But to be like thorough and just like follow the format, I'm going to follow the procedure from Cal 1. So now I'm going to find the critical points. Critical points, I take the derivative of that function and I just get what? Negative 1? Well, that's the slope of the line, right? What are we supposed to do with that? We're supposed to take that derivative and set it equal to 0, but it's never equal to 0, right? So this derivative equaling 0 doesn't ever happen, right? Because it's negative 1, which means I don't have a critical point. So if I want to find the max and min, I just have to plug in the 2 endpoints, 1 and 5. So now I just do the, I'm saying no critical points, so plug in endpoints. So what are the 2 endpoints? X is 1 and x is 5, right? So if I do that, I'm talking about taking the original function, and plugging in 1 for x, and what are we plugging in for y? 0, because we're still on L1, right? We're still on L1. So we plug in 1, 0, I'm going to figure out what that is, and then I'm going to plug in the other endpoint 5, and then 0 because I'm still on L1, and I'm going to look at those 2 values, and whichever one of these is the bigger one is going to be the max, and the other one's the min. So what happens when you plug in 1, 0? What do you get? You get 2. And what happens when you plug in 5, 0? What do you get? Negative 2. Okay. Hey, back from step 1. We're on step 2 right now. Back on step 1, what was our critical point? It was 2, 1? Yes. Okay, and when we plugged that into the original function, we got 1, didn't we? Okay, so right now we know that at this point we get a 1, and we know that along L1, The highest point you ever get is 2, and the lowest point you ever get is negative 2, right? I do not know yet if this is the absolute maximum for the entire surface we're looking at. I just know that along this line, that's the highest and lowest point. Was there a question? No? Okay. All right. I already know I'm going to throw this away because 2 and negative 2 are already, this is in between those two. So, but I'm going to keep going now. Let's go along L2. So if we go on L2, what does every point on L2 look like? They all have the same x-coordinate, right? What's the x-coordinate? 1. And then the y-coordinate is what? From 0 to 4, right? So watch how I write this. The x-coordinate has to be 1, and the y-coordinate can be any value y. I'm using y, not x. And my y here has to be between 0, right, and 4. Every point on L2 must have an x-coordinate of 1 and a y-coordinate that is bounded between 0 and 4. And then I play the same game. I say, let me plug this in to the original function and see what that output would look like. All right, I'm replacing x with 1 and y with y. So we get 3 plus y minus 1. Let me write it out. 3 plus x was 1 times y minus 1 minus 2y. So is this not just a line again? 2 minus y. This is a linear function, right? This is a linear function, but it is a function of a single variable. The variable is y, but it's still a single variable. And since it's linear, I'm not going to do the derivative this time. Do you all agree that I can just check the endpoints? Okay, so let's just check the endpoints. I'm going to write it down though. F prime of 1y will never be equal to 0 because it's linear, right? Linear. Because that's linear. The derivative cannot be 0 ever. And then I just check the endpoints. So when I say endpoints, I mean I need to check at 2 places. 1, 0, and 1, 4, right? So they both have the x-coordinate of 1, and the y-coordinate are the 2 extremes of the interval there. And 1, 0, didn't we already do 1, 0? Because that was this point. We did that earlier, and what do we get, 2? Okay, and then what about when you plug in 1, 4? Anyone do that yet? You got negative 4 or 1? You got negative 2? Let me see, I have the work here. So what was it, 1, 4, negative 2. You should get negative 2. So far, it's looking so far like 2 is the absolute max and negative 2 is the absolute min, right? That's so far. But we have one more boundary to move along. And I saved the best for last. I was waiting for everyone to get tired and sleepy. You ready for L3? The problem with L3 is that it's not a horizontal or vertical line. So you can't tell me that like here, we can say, oh, well, the y was always 0. And here we say, oh, the x was always 1. If you're along a line like this, then the x and y depend on one another. Yes?
But it's still a line.
It's still a line, yes. But yes, I'm not sure. It is a line. Exactly. Because it's a line, we should be able to express one of the variables in terms of the other. So let's investigate this a little bit more. You see this? This is a line. Since this is a line, this should have an equation that goes with it, right? Y equals mx plus b. Right? And I can find the equation of that line many different ways, but the way that I'm going to go about it is I'm going to I'm going to use the formula, the point slope formula. Okay, so I'm going to find this equation. I'm going to use this formula right here, y minus y1 equals m times x minus x1. This is a formula that will give you the equation of a line as long as you have the slope of the line and you have 1 point on the line. Right? You need a point and you need the slope of the line. I actually have 2 points, don't I? I can use either one. So which one would you like me to use, the 1, 4 or the 5, 0? 5, 0? I'm going to do 5, 0. Okay, so let me start with that. If I replace the y with 0 and I replace the x with 5, I get this. That's the equation line so far. I just need the slope, and the slope I'm going to get just by a visual. It's rise over run, isn't it? And we go from left to right. So rise over run, I actually have to go down by how much? By 4. This is 4, and then how far over? 4, right? Because you're going from 1 to 5, so that's 4. You're going from 4 to 0, so 4 down, 4 over. -1 is the slope, right? You could actually compute it, y2 minus y1 over x2 minus x1, compute the slope. But it's Cal 3, so I'm not going to do that. So -1 x minus 5. Let me distribute that negative through negative x plus 5. This is the equation of that line, right? Now, the reason that's important to me is because now I can express any point on this line as an ordered pair where the x-coordinate is simply whatever x-coordinate I plug in, and the y-coordinate is just that written in terms of x, right? If your x is this, then this is the y that comes out, right? Now, it's not as good as what we had previously. With the vertical and horizontal, you know, one of these was a constant. Here, they're both variable expressions. Anyone have a question on that? So we have this relationship. Now, we do have to talk about a restriction on x. Is there a restriction on x? 1 to 5, from 1 to 5. So 1 less than or equal to x less than or equal to 5. Okay. Now I'm going to do what I did before. I'm going to take that point and I'm going to say, hey, well, what happens if I take something that looks like that and I plug it into the original function? What do I get? So skipping down to here, if I take that, that format into the original function, I get, let me write it, 3 plus, okay, x is going to stay x, but my y's are being replaced with negative x plus 5, and then minus x, and then minus 2 times negative x plus 5. That's me rewriting the entire original function, leaving all x's alone, and replacing all y's with that linear function that I got. And let's just clean this up. Who has a question? Anyone? Multiplying things through.